All right, people. I believe everybody is doing great, nice, and absolutely fine. So, in this particular video, short video, we will be revising the entire modern physics. Okay, we will not leave any single topic. Let's first start with a chapter that is dual nature of matter and radiations. Okay, so in this particular chapter, the first topic that you might have seen is energy of a photon. Okay, we say, sir, if we have got a light source over here, so from that light source, light is coming out. We say these are the photons coming out because light is made up of photons, and those photons have got energy. Now the question is, what is the energy of a photon? We say h into f. H is Planck's constant, f is frequency. Okay, and we can also write it something like this: E, energy of photon, is hc divided by lambda, because frequency is c by lambda. C is speed of light, lambda is wavelength. Okay, then we have over here, you can also write the energy of photon as 2 into 10 raised power 25 divided by lambda in joules. So basically this is the energy of a photon in joules. Okay, so basically if you put the value of h over here, c over here, you'll get this value. So directly you'll remember this is also the energy of a photon, which helps you to find its energy in joules, and lambda is given in meters. Okay, now one more formula. Sir, we need to calculate the energy of photon in electron volts. Then this is the formula: 1240 divided by lambda. But here you have to take lambda in nanometers, and this will give you the energy of a photon in electron volts. Then you have got one more formula. Sir, energy of photon in electron volts. But if the wavelength of a photon is given in, we say angstrom, then we use this formula: 12400, lambda is given in angstrom. Okay, now let's move on to the next one, that is energy of light. Guys, we say light is made up of so many number of photons. One photon has got energy hc by lambda. N number of photons have got energy nhc by lambda. So that is the energy of light. Okay, let's talk about the power of light. Sir, power is simply energy divided by time. If you have the light source, how much energy is coming out every second, that will be the power. Energy divided by time. Okay, so what is the formula? Sir, nhc divided by lambda into t. N is number of photons, h is Planck's constant, c is speed of light, lambda is wavelength, t is time. This is how you find the power of light. Okay, next topic, we need to talk about intensity of light. Directly you will guys remember that intensity is simply power divided by area, or you can also say energy falling per second per unit area. And what is the formula? Formula is nhc divided by lambda t into a, or you can also write nhf divided by at. Now let's talk about the photoelectric effect. Sir, what is a photoelectric effect? When light falls on a metallic surface, we say electrons are ejected from that metallic surface. This is what we call the photoelectric effect concept. Okay, so basically when photons fall on the photosensitive metallic surface, electrons are ejected from that metallic surface. This is what we call the photoelectric effect. Then a small concept is what we call the work function. Work function means minimum energy required to pull the electrons from the metal surface. Like this metal surface has got 2 electron volt energy. Means if you have to pull out the electron from this metal surface, how much energy you should send over here? 2 electron volts. If energy of photon is less than work function, we say photoelectric effect does not take place. Similarly, this has got 5 electron volt work function. Okay, now experimental setup of photoelectric effect. My dear friends, if you take a look at the experimental setup, it is not like you'll go out in a sunny day and you say, sir, I'm wearing the shorts and I'll perform the photoelectric effect. No, so there has to be the proper setup. We take a tube like structure over here. Inside this we have a metallic plate. This is the metallic plate, which is what we call the cathode, and this is what we call the anode over here. Okay, now my dear friends, this is the light source. Photons fall on this metal surface, electrons come out of this metal surface and they start moving towards the anode. My dear friends, let's suppose we say we are sending an photon of 8 electron volt. 2 electron volt it is using in pulling out the electron from the metal surface. Rest of the energy will be used as kinetic energy. So we say rest of the energy, because of the rest of the energy, the electrons will move forward. Now my dear friends, can I say energy of photon is used in, we say work function. Work function is what? Work function is to pulling out the electron from metal surface, and rest of the energy which is used in kinetic energy that electron has to then move forward. So this is what we call the Einstein's photoelectric equation. Now guys, since the electrons are moving in this case in the forward direction, so we say photocurrent is being produced. Now my dear friends, if you plot the graph between photocurrent versus EMF, directly remember over here, sir, the graph will be something like this. As you keep on increasing the EMF, we say photocurrent keeps on increasing. Okay, at some point it becomes constant. That current is what we call the saturation current. That value of current is saturation current. And if you reverse the polarity of the battery, in that case we say, sir, photocurrent keep on decreasing. At certain value, photocurrent becomes zero. That's what we call the stopping potential. Okay, stopping potential is that potential at which no electron flows. Okay guys, I say electrons flow from cathode to anode. Okay, if I say stopping potential, we say no electron flows from cathode to anode. Keep that thing in your mind over here directly. Okay, now my dear friends, we have got the next concept, that is de Broglie wavelength or matter wavelength. De Broglie said that everything in this universe is a particle and is a wave also. Like I have got this car key over here. This is a particle and this is a wave. Okay, so we say it has got a wavelength. How much is its wavelength? Lambda by P. Lambda is Planck's constant, P is momentum. Okay, you can write P is equal to mv. Okay, so my dear friends, if there is a particle which is moving with some velocity, it has a wave associated with it. So that wave has a wavelength. How much is that? That is h by p. Now my dear friends, if somebody asks you, tell me the de Broglie wavelength in terms of kinetic energy, you will simply say, sir, that is h upon 2 mke. This is the de Broglie wavelength in terms of kinetic energy. Okay, now de Broglie wavelength for a relativistic particle. Relativistic particle is that particle which is moving with the speed of light. Okay, which is moving with a greater speed comparable to the speed of light. Okay, like electron, like proton. So we say it has got the de Broglie wavelength h under root of 1 minus v square by c square m naught into v. M naught is the rest mass, v is the speed of that particle, c is the speed of light. Okay, now charged particle accelerated under potential difference delta v, h upon under root of 2m delta v. It has got this much de Broglie wavelength. Okay, now if there is a charge placed in the electric field, how much de Broglie wavelength does it have? Lambda is equal to h upon qet. Q is the charge, E is the electric field, T is the time. Similarly, if you have a charged particle placed in the magnetic field, we say, sir, lambda is equal to h upon qbr. H is the Planck's constant, Q is the charge, B is the magnetic field, R is the radius in which that charged particle moves. Guys, if a charged particle enters the magnetic field perpendicularly, it follows the circular path. That circular path has radius r. Okay, now for a gaseous molecule, we say, sir, how much is the de Broglie wavelength? H upon under root of 3m kBt. Kb is the Boltzmann's constant, T is the temperature. Okay, now my dear friends, if there is an electron which is moving in the nth orbit of an atom, how much de Broglie wavelength does it have? We say n is the nth orbit, h Planck's constant, 2m into 13.6. Okay, now my dear friends, let's move on to the chapter number 2. That's what we say atoms over here. Let's talk about the atoms. See, first we need to talk about the Thomson's model of atom. What does Thomson's model of atom say? Thomson says that an atom is a positively charged, an atom is like a watermelon. So this was the model given by Thomson. Thomson said an atom is like a watermelon. Okay, seeds represent the electrons and the red portion that we eat represent the positive charge. Means he also said an atom is an electrically neutral sphere. Number of positive charge is equal to the number of negative charge. And my dear friends, most importantly, let me just tell you over here, in an atom, we say positive charge and mass of the sphere is uniformly distributed. It is not like at some point mass is more, some point mass is less, charge is more, charge is less. No, it is equally distributed at every point. Okay, and then we have the Rutherford's atomic model. So Rutherford basically performed an experiment, that is what we call the alpha particle scattering experiment. Okay, so in which, what did he say? So he took an alpha particle source which provides so many alpha particles. Okay, then he took a gold foil over here and then he took a deflection screen. Okay, so from this we say alpha particle source, we say beam of alpha particle is coming out, and this beam means so many alpha particles, they are directly crossing this gold foil and falling onto the screen. So in this experiment, what he observed is that 99.86% alpha particles are directly crossing and falling on the screen. Okay, only 0.4% alpha particles were deviating. What does that mean? 1 in 8,000 alpha particles was reflected back. Okay, if you are sending 8,000 alpha particles, only one is reflected back. This model basically indicates that the atom is not like a sphere in which positive charge is present everywhere. No. So he said positive charge is concentrated at a unique position at center called nucleus. Okay, so this is according to the Thomson's model. Okay, so we say and electrons are revolving around the nucleus, not randomly distributed. This was basically the Thomson's model. Then comes the Bohr's model of an atom. Listen to me very carefully. When it comes to the Bohr's first postulate, Bohr said that an electron is revolving around the nucleus. Okay, that is an accelerated motion. Yes. So means charge is accelerating. So whenever we say, sir, you have got a nucleus over here, you have an electron revolving around the nucleus, this is an accelerated motion. Okay, and my dear friends, it does not form the electromagnetic wave, because we say whenever the charge accelerates, electromagnetic wave is found. But he said that yes, here charge is accelerating, electron is accelerating, because circular motion is accelerated motion. It forms the wave, but it forms which wave? Stationary wave. So we say electron does not, so we say charge does not radiate energy. So my dear friends, in shortcut, what I'm trying to say is that Bohr's first postulate say if an electron is revolving around the nucleus, it does not radiate energy, it does not release energy. So it is basically revolving in stable orbits. Okay, Bohr's second postulate says that an electron is revolving in that orbit only in which its angular momentum is nh by 2 pi. N can be 1, n can be 2, n can be 3. Okay. So basically, this is the Bohr's second postulate. Let's talk about the Bohr's third postulate. Bohr's third postulate says that if an electron is revolving in the first orbit, if it makes the transition from first to second, we have to supply the energy to it. Okay, if it makes the transition from lower orbit to the higher orbit, and if the electron wants to make the transition from higher orbit to lower orbit, it will release the energy in the form of a photon. Keep that thing in your mind. Okay, now mathematical analysis of Bohr's model. Let's suppose, my dear friends, we say we have got over here an atom. Okay, this is the nucleus, and the charge is revolving, electron is revolving around the nucleus. If I say electron is revolving in the nth orbit, how much does its velocity, how much is its velocity in the nth orbit? We say its velocity is v is equal to v naught z by n. Z is atomic number, n is, we say, sir, the nth orbit. Which orbit you are talking about? Value of v naught is 2.2 into 10 raised power 6. Okay, now my dear friends, radius of an electron in the nth orbit. If an electron is revolving in the nth orbit, how much is its radius? So we say the radius it has, that is r naught n square by z. Okay, r naught is, we say, 0.53 angstrom. Next point we need to talk about over here, that is time period of an electron. Okay, how much time this electron takes in completing the one cycle? That is, we say, 1.51 into 10 raised power 16 n cube divided by z square. Keep this thing in your mind. Okay, one more thing, guys. If I say an electron is revolving around the nucleus, okay, so we say since the electron is in motion, it has got kinetic energy. How much kinetic energy does it have? Z e square upon 8 pi epsilon naught r. Keep this thing in your mind. Now guys, you have got the positive charge nucleus and electron. Whenever you have the two charges separated by some distance, they have potential energy. So we say, my dear friends, their potential energy is minus z e square upon 4 pi epsilon naught r. And my dear friends, they will be also having the total energy. Total energy in this case is minus z e square upon 8 pi epsilon naught r. Z is the atomic number, E is the charge on an electron, pi is pi. Okay, epsilon naught is epsilon naught, permittivity of free space. We say, sir, r is what? R is the radius over here. Okay, now my dear friends, if somebody asks you to plot the graph between plot the graph of kinetic energy, this will be the graph of kinetic energy, this is the graph of potential energy. In between these two, we have the graph of total energy. Okay, Now, my dear friends, one more thing I just want to tell you over here, that is, let's talk about the chapter nucleus over here. When it comes to the nucleus, my dear friends, nucleus is which is present at the center, okay? And the particles which are present inside the nucleus are called, we say, I forgot the name, that is nucleons. Yes. So we say that is protons plus neutrons make what? Nucleons. The particle inside the nucleus are called nucleons. And remember, radius of an atom is 10 raised power minus 10 meter and radius of nucleus is 10 raised power minus 15 meter. Okay. So my dear friends, the particles inside the nucleus are called nucleons. And representation of nucleus. How do we represent the nucleus? Let's suppose we have got a nucleus over here, X. Okay. At the top of it, we write A. A means mass number, and then we write over here Z. Z means atomic number. Mass number means, what does mass number mean? Mass number means number of protons plus number of neutrons, that is number of nucleons. And Z means atomic number. What does atomic number mean? Atomic number means number of protons only. Okay, so my dear friends, now rest mass energy. If I say I have got a mass over here and it is moving with some velocity, we say because of its motion it has got kinetic energy. Now if I say I have got a mass over here, okay, and because of this mass it has got energy in it, it has got energy associated with it, that energy is what we call the rest mass energy. And how do you calculate? That is mc square. E is equal to mc square. If I say I have got 10 kg object over here, tell me how much energy is stored in the 10 kg. You'll say, sir, m is 10 kg multiplied by c square. C is 3 into 10 raised power 8. So you can calculate that energy over here. And even that, this was the question asked in, we say, sir, NEET 2020. So that is, find the energy associated with 0.5 gram of substance. You can calculate. So you can use the formula E is equal to mc square. You can find it. Next is nuclear size or size of nucleus. So when it comes to the size of nucleus, we can directly say, guys, as more the number of nucleons inside the nucleus, more will be, bigger will be its size. Okay, bigger will be its size. Less the number of nucleons in the nucleus, less will be its size. Okay, now listen to me very carefully. We say, sir, volume of nucleus is proportional to the mass number. Okay, sir, more is the mass number, more is the number of nucleons, bigger it will be, more volume it will have. So we say here r cube is proportional to a, so r is the radius, so r is proportional to a raised power 1 by 3. So if you plot the graph between r, that is radius of nucleus, versus mass number, so that will be something like this. R is equal to r naught a raised power 1 by 3. This is what we call the nuclear size or nuclear density. Sir, what is nuclear density? That is, nuclear density is simply mass of nucleus divided by volume of nucleus. Mass by volume is density. Okay, and that is constant for all nucleus. So we say 10 raised power 17 kg per meter cube is the nucleus density of the nucleus. Okay, now we have the concept, that's what we call the binding energy. My dear friends, what is binding energy? Let's suppose if you have got a nucleus over here, okay, and it has got a mass number of nucleons is a, and number of protons is z. If you break this particular nucleus over here, after breaking, you observed that, sir, mass of z protons is zmp, mass of, we say, sir, a minus z neutrons is how much? We say, sir, a minus z into mn. So guys, what I'm trying to say in this particular case, if you break a nucleus, after breaking, you measure the mass of those nucleons present inside it, that came out to be greater than the collective mass, that came out to be greater than the mass when these protons and neutrons were inside the nucleus, simply. So that is what is mentioned over here. Okay, zmp plus a minus zmn is greater than m. What is that? Let me show you. The energy which is used in breaking the nucleus is stored in the form of mass. If this is a nucleus, you break the nucleus, okay, the energy used in breaking the nucleus will be stored in the form of mass. That's why when you took those nucleons out, their mass has increased. Okay, so we say, my dear friends, this energy is what we call the binding energy. This energy is what we call the binding energy. Simply. And if you say, if somebody asks you how much is the mass defect, you say, sir, zmp plus a minus z into mn minus collective mass. Okay, This is the individual mass, final mass minus collective mass. And if somebody asks you find the binding energy, delta m into c square, you will put the value over here, multiply it with the c square. Okay. Then, my dear friends, there is a graph between, we say, binding energy per nucleon versus mass number. Like the graph is something like this. This is binding energy per nucleon. And remember one more thing, binding energy per nucleon means stability. More is the binding energy per nucleon, more is the stability. Okay, binding energy per nucleon means how much energy you need to apply to take out one nucleon from the nucleus. That is binding energy per nucleon. Okay, now, so we say binding energy per nucleon versus we say mass number. My dear friends, experimentally the graph came out to be something like this. Those nuclei which have got the mass number less than 30, see on this axis we plot mass number. Those nuclei which has got the mass number less than 30 are called lighter nuclei. See, it is mentioned over here. Those nuclei with mass number less than 30 are called lighter nuclei and are unstable. Okay, and those nuclei with mass number greater than 170 are called heavy nuclei. This is heavy nuclei and these are also unstable. Now my dear friends, see, those nuclei which lie between A is equal to 30 to A is equal to 70, these nuclei are stable. Now guys, if you have got the two nuclei over here which are unstable, so they will fuse together, join together to form a bigger nucleus so that they attain stability. So this process is called the fusion. So fusion is only to attain stability. And if you have got a bigger nucleus, it will break into two smaller nuclei so that it comes under this range, A is equal to 30 to A is equal to 170. So this process is what we call the fission. So this is also, we say, in order to attain stability. Fission is also the process in which nucleus attains stability. Okay, then we say Q value of the reaction. What is Q value of the reaction? Let's suppose we have got the two nuclei A and B. Okay, these are the reactant nuclei. These two nuclei are converted into C plus D. So this is some sort of reaction. Okay, and in this reaction we say plus Q. Q is the energy absorbed or released during the process, during this reaction. These are reactant nuclei, these are product nuclei. And if somebody asks you how to find the value of this Q value of the reaction, you say, sir, mass of the reactants minus mass of products. Okay, these are reactants, these are products, multiply with C square. Okay, and my dear friends, one more important thing is you can find the Q value of the reaction in terms of binding energy also. How? See, that is binding energy of products, binding energy of C plus binding energy of D minus binding energy of reactants, binding energy of A plus binding energy of B. So keep this thing in your mind. In a reaction, if you have to find the Q value of the reaction, you can find with the help of this equation. Okay, so this was all about it. All the important concepts have been discussed in this particular session. So thank you so much. Take care and bye bye. In 22 minutes, complete modern physics have been done. So let me know in the comments which chapter you want next, so I'll be making for that chapter next. Okay, let me know in the comments, everybody, and do like this session, share this session. Thank you so much.